Hello everyone and welcome to Physics 220 here at Grantham University. This is Lesson 6 lecture, and this week is going to be all about waves. Our first concept we start with is frequency, period, and wavelength. So some of the basic properties of waves are, as mentioned, frequency, period, and wavelength. Period is the amount of time for one complete cycle, usually denoted by a capital T in your text, and measured with a time unit, usually seconds. The inverse of this is called the frequency, and is the number of cycles per second. That's denoted usually by a small f and is measured in insert seconds or hertz. Now, if you imagine the period, if you imagine watching a wave, it's the amount of time it takes a full wavelength to pass out. The frequency is if you imagine yourself standing at one point and watching waves pass by. It's how many waves are going to pass per unit time. Because of this inverse relationship, we can write period or t as 1 over f, or we can write frequency f as 1 over t. Lastly, in our first definitions here, we have the wavelength, and this is defined to be the length from one identical point in a wave to another, usually measured from trough to trough, for example. It's denoted by the Greek letter lambda, and is measured in some sort of length, meters, for example, but can also be down to millimeters, nanometers, micrometers, or so on. Our next point of interest here is a nice application of a simple principle that helps us model waves, and it's called Hooke's law. This is an example of a mass on a spring, and it's a great way to see simple harmonic motion and then model it to waves in general. So you imagine a horizontal mass on a spring moving back and forth in a frictionless surface. Then we see the restoring force is linearly proportional to the displacement from equilibrium, or F equals negative kx. The negative sign here is key. What this means is that the force from the spring always pulls in the opposite direction of the motion from equilibrium. So if you were to imagine yourself pulling the spring to the right, the force pulls back to the left. And if you imagine yourself compressing the spring to the left, the force pushes back to the right. The other thing to note is that the further you pull or push, the stronger the force gets. That's why I say the force was linear proportional to the displacement. Continue our examples here. We know, looking at Hooke's law, that K is what is called the spring constant. K has units of newtons per meter to be consistent, meaning if you look at the relationship, K equals F over m, so it has to have units of newton per meter. It also is related to how energy is stored in the wave, or U equals 1/2 kx squared, and this is the spring potential energy. Remembering that F equals negative kx, and we remember all the way back to Newton's second law that F equals ma, we can get a relationship between K and x, or negative kx equals ma, or we can write ax of t as negative k over m times x of t. In general here, we see the solution for the simple harmonic motion can be described as a cosine function. X of t equals a cosine omega t, where omega squared is k over m. And we also see that a is the amplitude, and usually measured in a distance unit, and omega is what's called the angular frequency, which we saw a few weeks back. This also means that the regular frequency of oscillation is given as f, the frequency, is 1 over 2 pi, the square root of k over m. So now I want to touch on a couple more interesting facts. So the first is the types of waves there are. Turns out there are two types of waves they are called transverse and longitudinal. So transverse waves moves the medium perpendicular to the motion of the wave, and a longitudinal wave moves the medium parallel to the motion of the wave. So a good way to envision both of these is with a very large spring. So if you pull the spring relatively taut and shake it up and down and make like a sine wave that moves back and forth, that would be considered a transverse wave. For a longitudinal wave, pull the spring even tauter and then pull it back just a little bit more, and the spring that kind of bounces back and forth, that would be what's known as a longitudinal wave. Now our next concept is what's called the wave equation, and this states the velocity for a wave is equal to its wavelength times its frequency. And one thing to point out that's extremely useful, since this is true for all waves, and if we have a special case for light, the speed of light is always 3 times 10 to the 8 meters per second. And this is important because all you need to know is either the wavelength or the frequency, and you can determine the other. Here's an example that illustrates that. We say the frequency of a light wave is 340 megahertz. What is the wavelength? So remember that lambda from our equation above then would be v wave over f. And if we say what's the speed of light for the speed of the wave for light, we get that v wave is 3 times 10 to the 8 meters per second. So we put lambda equals 3 times 10 to the 8 meters per second divided by 340 times 10 to the 6 hertz. Remember, mega means 10 to the 6. And our answer then is 0.88 meters, or we can even say 88 centimeters. So there's an example of how you can use that equation, especially for light, and get a useful practical result out of it. So now I want to focus on some of the properties of sound waves for a few seconds. First, we see that they are longitudinal waves. I talked about this a little bit. They have areas that are more dense. These are called compressions, and areas of lower density called rarefactions. And also a very interesting point is that the speed of sound is completely dependent upon the temperature of air and density. So we see that for where most cases the density of air is about the constant, the velocity of sound is 331 plus 0.606 times the temperature in Celsius meters per second. So most of the examples we do here in the book, we assume a temperature of about 25 degrees Celsius, and that usually gives us a velocity for sound of about 342 or 343 meters per second. Now, when we deal with sound levels and intensities, one of the things that they have come up with is to work with a system what's called decibels. And sound intensity, then, like I said, is measured in a unit called decibels. The reason they do this is human hearing is not linear. It's actually logarithmic. So when something sounds twice as loud as something else, it's actually many, many times louder than that. So we compare these sounds to what's called the quietest sounds human can hear, or called the threshold of human hearing, called I0, and it's done in an equation like this. Beta, the sound intensity in decibels, is 10 decibels log to the base 10 of I over I0, with I being the intensity of your source, and I0, again, which is called the threshold of human hearing, which is 10 to the minus 12 watts per meter squared. Well, that covers everything for this week in conjunction with the written lectures also. Please review those, and if any time you have any questions, email your professor and they'll get back to you quickly.
Well, actually, now that I think about it, I'd like to do an example before we wrap up for this week. So here's a decibels example. Remember we saw on the previous slide that the decibel rating is 10 decibels log 10 I over I0. Remember, I is the intensity of your source, and I0 is the threshold of human hearing. So here's an example. The sound of a band is rated as 60 decibels at a distance of 10 meters. What is the decibel sound level of the band when it is 20 meters from the band? Okay, excuse me, one is 20 meters from the band. So this is a little bit of a tricky one. I'm going to walk us through this one. So the first thing we have to do is kind of break apart the decibel using the equation and determine the intensity of the band. So if 60, remember the equation is the decibel rating is 10 decibels log base 10 I over I0. So we plug in our value here of 60 decibels and get this is equal to the standard 10 decibels log 10 I over I0. Canceling the 10 decibels out, we get 6 equals the log of base 10 of I over I0. And to undo a logarithm, you have to exponentiate it, and you take it to the take the number to the power of the base, so it's a log base 10. So to undo that, I'm going to raise both sides to the 10. So the left-hand side becomes 10 to the 6th, and then the right-hand side becomes just I over I0, which now we can isolate that I out and solve for what we're looking for. Or if we remember that I0 is 10 to the minus 12 watts per meter squared, the intensity of our sound here, the band at 20 meters, is going to be 10 to the minus 6 watts per meter squared. Okay, so now what we want to do. We still are looking for the decibel rating for the band when they're 20 meters away. But the thing that's important here is you can't just change the decimals by a factor of 4 because it's 1 over the distance squared. It's the intensity you have to change by that factor. So you notice here now you take the intensity at 20 meters is the intensity at 10 meters divided by 4. So dividing 1 times 10 to the minus 6 by 4 will give us 2.5 times 10 to the minus 7 watts per meter squared. So now we've got the intensity at 10 meters. So, and this is where it's almost like reverse engineering. To get the answer back at this point now, we had to plug this back into the original decibel equation of 10 decibels log 10 I over I0. But this time, you notice we're going to be plugging in for the I there, we're going to be plugging the intensity at 20 meters. So we get 10 decibels log 10 of 2.5 times 10 to the minus 7 watts per meter squared divided by 10 to the minus 12 watts per meter squared, and that will give us a decibel rating of 54 decibels. A couple things I wanted you to note. One, notice that the decibel rating, since it is logarithmic, it only went down 6, and that's actually a pretty good description here. Is whenever you move twice as far away from something, the decibel rating drops by a factor of 6. And then note that the reason why we have to use this, and I mentioned this before, is because human hearing is logarithmic. It's not linear. So that something that appears twice as loud is actually many, many, many times more intense. It's because of this logarithmic ability of the human eyes. Eyesight does this also. We haven't got into that yet, but when something appears twice as bright, it's actually many, many, many times more intense. And this leads to some complications with stellar magnitudes and things like that. But anyway, back to this problem. We see our decibel rating and how this actually can help us solve some problems. So the next thing I want to show here are some various decibel levels and how they compare. Again, there's a kind of a warning. Any prolonged exposure to 85 decibels or higher can cause gradual hearing. So notice a recreational vehicle 70-90, subway or motorcycle about 85, lawnmower about 85 to 90, train garbage truck about 100, newspaper, farm tractor, so on and so forth. And again, now above 100 decibels, exposure of this more than 1 minute risks permanent hearing loss. A jet flying over 100 feet is about 103. Snowmobile, jackhammer, thunderclap. Now they say stereo 110 to 125. Obviously that's going to be a function of how loud you have it. Rock concerts 110 to about 140. Jet taking off, shotgun firing about 140. A boom cars about 145. Now, if we look at some of the lower values, we see that a diesel truck is about 85, garbage disposal, city traffic noise about 80. Then we get a washing machine down at 78, a dishwasher at 75, all the way down to normal breathing, which is about 10 decibels, going up a little bit more again, rustling leaves or mosquito about 20. So you notice, again, since this is a logarithmic scale, there's a varying level of what we know what the noise level sounds like, what we're accustomed to, like a quiet office is about 50 to 60, laughter is about 60 to 65, up to a dishwasher about 75. But when we go back up to the high levels, the numbers are about twice as big. Notice 120 decibels for a thunderclap versus a 60 for a quiet office. But they're many, many more times than just twice as loud. And again, that plays into the whole logarithm natures of how sound levels work and how we're affected by them. Well, that's it for the lecture portion this week. Again, make sure to peek in and look at the lab section of the class. And if you have any questions at any time, please contact your instructor.